Hello and welcome uh, to the video lecture series on chemistry of heteroaromatic compounds. Last time we were talking about the retrosynthetic analysis and synthesis of several furan derivatives. In that discussion আমরা দুটো মেন রিঅ্যাকশন নিয়ে ফোকাস ছিলাম। একটা was Paal-Knorr synthesis, the other was Feist-Benedict synthesis, through which we could make substituted furan nucleus. Today's topic of discussion is the retrosynthesis and synthesis of the other 5-membered heteroaromatic ring featuring one heteroatom, that's pyrrole. So we have 4 carbon atoms and 1 nitrogen. So you can think that because formation of this carbon heteroatom bond is relatively easier, we can disconnect here and also here. That will generate a fragment which will be electrophilic at both ends, and I have to have a nitrogen which will act 2 times as a nucleophile. Such a fragment where there is electrophilicity on C1 and C4 is undoubtedly a 1,4 dicarbonyl, and this nitrogen can be supplied by either ammonia or by a primary amine, something where there are a couple of hydrogens present on the nitrogen which will eventually be lost. If I do this reaction with ammonia, then I will end up with NH, and if I do it with RNH2, I will end up with a substituted pyrrole, N-substituted pyrrole, Rn. The mechanism can be predicted, but the exact sequence of events for a particular and specific example will be rather difficult to pinpoint. You have a 1,4 dicarbonyl, so an amine can undergo nucleophilic addition to any one of these carbonyls. Supposedly, if these 2 carbonyls have equal electrophilicity, then at any one position the nucleophilic addition will take place. Or if one carbonyl is slightly more electrophilic than the other, then RNH2 will preferentially attack here. Regardless of the choice of the position of attack, it will attack one of these carbonyls, and I will get a carbinolamine derivative, which is also a hemiaminal. This might choose to eliminate a water molecule from here, so I get an amine type derivative, or a second nucleophilic addition may ensue where I will get another intermediate where this nitrogen has done its due diligence and it has attacked 2 times, performed its nucleophilic addition 2 times, and I have already constructed the 5-membered ring. All that remains is to lose the 2 molecules of water from here, and it will undoubtedly be assisted by this nitrogen lone pair. So this nitrogen lone pair will push here and this OH will go away, and then the hydrogen proton will be lost, and I will get a double bond here, and I will get a nitrogen lone pair here, etc., etc. That may very well happen, or the enamine type derivative that may choose to close down the ring now by the second nucleophilic addition, and then water is lost, and I will get the same pyrrole derivative that I got from this addition compound. The mechanism, as I have told you, will be roughly something like this, but which pathway is actually operating, that is dependent upon the pH, the solvent, the amine itself, and the dicarbonyl structure, especially the ring closing step, whether the nitrogen ring closes down the ring before losing any water molecule, or does it lose water and then closes the ring and then finally loses the second molecule of water to give you the aromatic ring is all are possibilities, all can be explored. So this is very much like the Paal-Knorr synthesis of furan, where we had a 1,4 dicarbonyl ring closing down on itself by one oxygen acting as a nucleophile and the other carbonyl acting as an electrophile. So these examples feature, we have ethyl acetate, we are making an anion from it, and with two equivalents of such molecules, if I add one equivalent iodine, one of them will experience ampolang, the other will make a nucleophilic attack, will form the crucial 1,4 dicarbonyl compound, from which the hexane 2,5 dione can be liberated by knocking out these two carboxy groups. Hydrolysis followed by decarboxylation will do that, and then you treat it with ammonium carbonate, which is a source of the in situ ammonia, to give 2,5-dimethyl pyrrole. The hexane 2,5 dione can be combined with aniline in methanolic HCl medium, and you do that, you get the corresponding N-phenyl 2,5-dimethyl pyrrole. The same hexane 2,5 dione can be treated with RNH2 so that the NR derivative N-alkyl 2,5-dimethyl pyrrole can be generated. Here we have a 1,4 dicarbonyl where two phenyl groups append the chain ends. This is 1,4 diphenyl butane 1,4 dione. Doing this reaction with ammonium carbonate in DMF medium closes down the ring so that we get 2,5 diphenyl pyrrole. So you can have acid catalyst present, or sometimes heating with ammonium carbonate only is sufficient. Okay, so this makes sense because we have already seen that you can think of 1,4 dicarbonyl compounds as a bisphenol type thing, and then if you dehydrate, take away the water molecule from here, you will get the furan nucleus. But we know that primary amines and ammonia, they have a tendency of forming imine linkage with carbon-carbon double bond, with carbon oxide double bond, and therefore they have this nucleophilic activity. So this reaction is not surprising. This can very well happen. Here are a few more examples here. You have taken resorcinol. The tautomeric form of resorcinol is this, where the carbon-hydrogen double bond can be chemoselectively reduced under catalytic hydrogenation condition. This gives access to the cyclohexane 1,3 dione, which when treated with base will undergo deprotonation, and then subsequent alkylation with alpha bromo acetone will give access to the corresponding 1,4 dicarbonyl compound. Look carefully, this from acetone, when you have prepared this, you have done your ampolang, as you should have, because construction of this 1,4 dicarbonyl will require ampolang at some stage. And now you can close down the ring with RNH2 so that you get a bicyclic pyrrole derivative. This molecule is the bis-acetal form of succinaldehyde. If you treat this with a mild acid like acetic acid, then it will open up. Under this reaction condition, this will open up, will give you succinaldehyde. Succinaldehyde is a 1,4 dicarbonyl. When treated with amines such as this, the stereocenter of this amine molecule will be preserved, the nitrogen will be incorporated in the ring, and we will get a N-substituted pyrrole. This one here is an elaborate 1,4 dicarbonyl where you have two functionalized phenyl rings on the two chain ends, and doing the reaction in presence of formic acid at 145 degrees centigrade, heating for 4 hours. Ammonium hydroxide is the source of the ammonia here, closes down the ring. Here we have a unique example where a furan nucleus is present and NH2 group is also present, which will act as a source of the pyrrole nitrogen. If you treat this with hydrochloric acid in acetic acid medium, say for example you keep it over a day, for a day you keep it in contact with acid, this furan ring will actually open up, because we know that furans are enol ethers susceptible to acid hydrolysis, so this will open up. And this nitrogen will now act as a nucleophile and close down the ring so that I get this elaborate structure. So the furan ring opens and the pyrrole ring closes. Furan ring is aromaticity is a little bit less. The pyrrole ring is a little bit more aromatic. So that could be the driving force of this reaction. Here again we have another 1,4-dicarbonyl where there is yet more functionalization. We have a pyridine ring, we have a parafluorophenyl, dutifully closing down the ring under ammonium acetic acid condition so that the derivative is formed. This time we do not have a furan, it looks like a furan, it's kind of a dihydrofuran and it's actually a hemiacetal. So this time if you do this ring with ammonium acetate and ethanol, this will open up in this medium, this ring will open up so that I get the corresponding formaldehyde and not formaldehyde but the aldehyde derivative, and when this opens up this actually generates the carbonyl on the other side, so I get this nice 1,4-dicarbonyl where one end is aldehyde, the other end is the keto. Ammonia will most definitely will attack first here and then it will attack here and then the ring will close. Here again we have another unique example where the 1,4-dicarbonyl is generated in situ by the ozonolysis. We have a double bond here and I also have on this oxygen I have a tri-isopropyl silyl protecting group. You should be familiar with these protecting groups from your studies in relation to protecting groups when we discussed organic synthesis. So you have a carbon-carbon double bond here, so you do a ozonolysis and this breaks this thing apart. So this generates a CHO and that generates a carbonyl. That's basically a non-oxidative workup. And if you redraw the molecule in such a way that this aldehyde and this keto, they are brought closer to each other, that's basically an S star, that's a keto S star, and that's an aldehyde. So this one is highly electrophilic, that one is highly electrophilic, this one here is a little bit less electrophilic. Moreover, we have 1, 2, 3, 4, 1,4-dicarbonyl relationship between those two, 1, 2, 3, 4, 5, 1,5-dicarbonyl relationship between those two, and 1, 2, 3, 4, 5, 6, 1,6 relationship between those two. So even though I have 3 carbonyl groups onto this molecule, there is only 1,4 relation, and ammonium carbonate will close down the ring very nicely. I will get the functionalized pyrrole nucleus. So from these examples it should be evident to you that the Paal-Knorr synthesis of pyrrole is a very robust technique through which many functionalized pyrrole nucleus can be prepared. Next comes the two complementary method. One is the Hantzsch synthesis and other is the Knorr synthesis. This time we choose to disconnect 2 atoms at a time. So from the right side of the molecule we take apart these 2 carbon units, and from the left side we are left with 2 carbons attached with 1 nitrogen. There are 2 possibilities. The nitrogen will always be negative. Along with that you can have C del plus on that fragment. If this is your combination, then this 2 carbon unit will obviously be a del minus and del plus kind of thing. And if you choose to disconnect in such a way that the nitrogen is nucleophilic but the carbon on that fragment is nucleophilic as well, then obviously in this case you have a bis electrophile, a 1,2 dielectrophile. What sort of synthetic equivalents or synthetic reagents are we looking for here? Then if this is like that, then I have a nitrogen nucleophilic and a carbon, 1 carbon removed from the nitrogen as electrophile, then it could be alpha amino ketone. And this C del plus and C del minus, that could be represented very nicely by a beta geta star. In that case, you have to have the dehydration performed. And recall from our discussions in furan, if you adjust the oxidation level of these two carbons, then the triple bond being present here, this makes it susceptible to nucleophilic attack. At the same time, it generates a negative charge here, which is accommodated by the CO2, which means that this can function as a nucleophile. So this C del plus C del minus is obviously very nicely represented here, and also a double bond will remain. Therefore, that precludes any need of dehydration. So the dehydration step you can avoid. That's the Knorr synthesis. Okay, that is the Knorr synthesis. So it looks very simple. I have a alpha amino ketone, and the beta keto ester will react. This nitrogen will function as a nucleophile. This will attack here, so this will go away, and this will, it will become minus, and this will attack here, so that ring closes, and etc. etc. Sequence of events is obviously, there are possibilities, and you get a functionalized pyrrole derivative. So just like that. So it's attacking here, we get a carbonyl again here. Then with assistance of this nitrogen, this water molecule will leave. I have an enamine. This enamine will undergo ring closure, and then finally I will lose the water molecule, and I will get the corresponding target. But there is a huge problem here. The problem is that the alpha amino ketone, it contains a reactive nucleophilic NH2 and a reactive carbonyl, and therefore it has this unfortunate tendency of undergoing self-condensation. The alpha hydroxycarbonyl compounds are not like that. They do not undergo ring closing by themselves, but nitrogen being more electrophilic, more nucleophilic than OH, these alpha amino carbonyls are very, very susceptible to this self-condensation reaction, which will eventually lead to dihydropyrazine derivatives. So that's your Knorr synthesis gone. You can't possibly expect this molecule to survive this reaction condition. Once you have that, you must have the ethyl acetate or any sort of 1,3-dicarbonyl or any kind of molecule that represents this C del plus C del minus syntone present in the reaction medium, so that this will preferentially react with that beta keto ester or the alpha beta unsaturated or the ester which has a triple bond between the alpha and beta carbon. In the presence of these reagents, only the alpha amino ketone has to be liberated. If the alpha amino ketone is liberated where these molecules are not present, then it will choose to undergo self-condensation. And there are several techniques through which you can do that. You can take a alpha amino ketone salt. This nucleophilicity is not there anymore, and then you are reacting it with beta keto ester where the carbonyl carbon's electrophilicity is still enhanced by the introduction of a CO2 amine group here, and treat that with aqueous KOH so that your NH3 plus becomes NH2. Aqueous acid workup will give you this compound, which will eventually lead to loss of the two CO2 and CO2H groups with formation of the 3-methyl here. The ester is hydrolyzed, and then you heat it with H3O plus. First you lose the alpha CO2H, and then you eventually lose the second CO2H from the beta carbon. You can take the oxime derivative. So that's the oxime derivative. That's basically achieved. That basically has been achieved by the nitrosation of the alpha position of acetone. And as we know that nitroso is in automatic equilibrium with the corresponding oxime. You treat it with ethyl acetate, and the ethyl acetate's ketocarbonyl being more electrophilic, the nitrogen will attack here and eventually close down the ring to give you this. If I am to take 2 equivalents of ethyl acetate and then treat it with 1 equivalent of sodium nitrite in presence of acid, one of them will undergo oxime derivative formation at the active methylene position. This one being the more acidic, the enol is more stable here, and therefore you get an oxime here. and that oxime is liberated. Previously it was liberated by Na2H2O4, and this time it is liberated by zinc acetic acid. So it's a reducing environment from which you can reduce the oxime to liberate the NH2. To do that, combines with other ethyl acetic acid being present in the molecule, and this one here is actually known as Knorr's pyrrole, because Ludwig Knorr, when he developed this method, he himself reported this formation of this molecule. So this part is coming from one ethyl acetate, that part is coming from the other ethyl acetate, and this nitrogen is coming from, it's coming from the NaNO2, and you are doing this reaction via Knorr's synthesis. You are not making the 1,4-dicarbonyl first and then you are combining with nitrogen, because had you done that, then this methyl and CO2 would have been, this methyl and CO2 would have exchanged their position, because I would have got something like this. You remember that? This one. If you close down on this ring, then you will get the derivative where you have methyls at the 2 and 5 positions and 2 CO2 groups at C3 and C4. If you choose to do this with acetyl acetone with the oxime derivative of ethyl acetoacetate, then you will end up with this one, where we have COMe group here at the C3 and at C2 we have the methyl. The oxime derived from the other ketoester, where the ester is not ethyl but tertiary butyl ester, and I have 1,3-dicarbonyl present here, which will act as a C-del minus C-del plus synthon. Reduction is done in presence of palladium and hydrogen, so catalytic reduction will expose the NH2, ring closing, etc., will happen to give you this. So that's the Knorr's method done. Now here comes the Hantzsch synthesis. In Knorr's method, we have C-del minus C-del plus, and this time we are having C-del plus C-del plus. So that's basically the bis electrophile, and for that we need complementary nucleophilic reactivity here, and nitrogen is always the nucleophile. So if you go back a little bit and recall the discussions on furan synthesis, then we talked about the 5-spinary method. 5-spinary method is something where you have oxygen nucleophilic reactivity, carbons nucleophilic reactivity, combining with the bis electrophile, where 1,2 carbons are, the adjacent carbons are electrophiles. So that's the 5-spinary method. We choose to do this reaction with beta ketoester, where this oxygen was supposed to be incorporated in the ring, and the alpha haloketone, which will supply the C-del plus fragment. So the Hantzsch method is very similar to the 5-spinary. Here, instead of beta ketoester, you take an enamine, and with this electrophile you have alpha haloketone. So it is expected that when you mix the ethyl acetoacetate or the active methylene compound along with alpha haloketone, and you do the reaction in presence of ammonia, if this ammonia can function as a nucleophile, then it will attack this carbonyl, ester carbonyl, to form the carbonylamine, use a water molecule to give you the enamine. Enamines are excellent nucleophile as far as alpha haloketones are concerned. So the SN2 reaction will take place, eventually gives rise to the enamine, where we also have the opportunity of ring closure. So this ring closure will now take place to give you the corresponding Carbenolamine again, losing water molecule will give you this compound. So do the reaction with ethyl acetate and alpha chloroacetone in aqueous ammonia, you end up with this thing. So this part is coming from alpha chloroacetone, that part is coming from ethyl acetate, and this part is actually being produced in the reaction medium, incorporating the ammonia to the corresponding enamine derivative of the ethyl acetate molecule. Now you can choose to have preformed enamines and then react it with alpha bromo carbonyl compounds. You can do that. So this molecule has been synthesized in this way. And if you don't do the preformed enamine route here, it is actually observed that if I mix this alpha cyanocarbonyl and the alpha bromo ketone here in presence of ammonia, just as we did here, ammonia, instead of acting as a nucleophile, will choose to act as a base, and because the electrophilicity of this carbonyl is extremely high due to the presence of these two electron withdrawing groups, this will undergo a furan nucleus synthesis via aldol followed by O-alkylation. That's just like 5-sphenyl. So there is always a possibility that ammonia can choose to not react as a nucleophile but as a base, and if that happens, then you are not going to end up with the 5-membered heteroatomic ring with nitrogen. You are going to end up with a furan nucleus. And that's always a risk that you run with the Hantzsch synthesis. So the Hantzsch synthesis and the Knorr synthesis, they are kind of complementary to each other, because in Hantzsch synthesis you have C del plus and C del minus, and you are going to include a nitrogen here, so this is N minus and then it becomes C minus, and the alpha haloketone, that carbon is C del plus, that carbon is C del plus, and then you are combining this. So if you have a CO2 present here and your other other substituents are present here, so you have formation of enamine followed by SN2 followed by ring closure, so you end up with this thing. So I'm supposed to draw a R here. There should be a R here, okay? There should be a R here. So you have this alpha chlorocarbonyl where you have the R group placed at C2 and the CO2 at C4. The same reactant combination can combine in different ways. So the alpha halocarbonyl can undergo nucleophilic substitution at the alpha position by ammonia, so that you get a alpha aminocarbonyl, and this alpha aminocarbonyl represents the N minus C del plus synthon, and the beta keto ester in that case will represent the C del plus and C del minus synthon. These two can combine, and if they combine, then it is the Knorr synthesis that we are talking about. We get a regioisomeric pyrrole. Okay, so that's something which you need to think about, that under which condition these two reactions can compete, or suppressing one will require tinkering the reaction condition. This is in fact very much reminiscent to what we have seen for furan already. We can choose to do the 5-splenary method, that is the aldol followed by O-alkylation, by choosing the appropriate reaction condition, aqueous medium, NaOH being present, SN2 is deliberately being suppressed, aldol being promoted in the more polar reaction medium. We have already talked about this. Or you can choose to promote the SN2 reaction first, so that 1,4-dicarbonyl is generated in the reaction medium, so that the reaction course gets to diverted into the Paal-Knorr channel, so that two different isomeric furan derivatives are prepared. So the same thing is happening here. Let us take an example. If you have alpha bromoacetone and then you are thinking in terms of the Hantzsch synthesis, Hantzsch will require formation of the enamine, and till then this thing has to survive and wait patiently. So you are mixing these things up. You are doing the ethyl acetate mixed with ammonia and then adding the alpha bromo acetone. Enamine is formed in situ, ring closing take place, and you have this ethyl ester of 2,5-dimethyl pyrrole 3 carboxylic acid. So you have 2,5-dimethyl, and at 3 position you have CO2. But suppose you divert this and do the reaction where you promote the Knorr synthesis. For the Knorr synthesis, you don't need the enamine, but you need the alpha aminoketone. So you must have a nitrogen nucleophile here. That can be done by the Gabriel thalamide synthesis in presence of potassium iodide, which will act as a nucleophilic catalyst. Because recall, Gabriel's thalamide synthesis is basically an SN2 reaction at the alpha position of a carbonyl. If you choose to react alpha halocarbonyl as an electrophile. So where the thalamide ion, the potassium salt of thalamide will act as a nucleophile. If you choose to react with Rx, then you will get the N-alkyl thalamide, which on hydrolysis will liberate your primary amine. These things we know. And potassium iodide is a known nucleophilic catalyst. Therefore, you have this nitrogen being included here, and the thalamide group is also attached. You can remove that by hydrolysis so that your alpha aminoketone is revealed, and you take it as a salt so that the self condensation is prevented. And the same ethyl acetate can now function as a C-del plus C-del minus unit, and this is under basic condition N-del minus carbon C-del plus unit. They will close down the ring, and you will get a 2,4-dimethyl 3 furan. I keep repeating furan. I'm sorry, 3,2,4-dimethyl. This is 2,4-dimethyl, and you have at the 3 position you have this carbotoxic group. So this is a ethyl ester of 2,4-dimethyl pyrrole 3 carboxylic acids. Obviously these two are isomeric in nature. So it depends upon the reaction condition which you choose to react with, and then which of these regioisomeric pyrroles will form, you can decide. Just as you decided when you did the competitive reaction by tinkering the reaction condition, whether it follows the Paal-Knorr method, whether it follows the Fries-Binary method, what you did to get regioisomeric furans, you can also do it for the regioisomeric pyrroles. So there are many other ways through which pyrrole nucleus and furan nucleus can be made, but we will be stopping our discussion here. Pay particular attention to the skeletal disconnection, this type of things. People always keep asking questions from this, and they can give you a specific target molecule and ask you specifically that prepare this from ethyl acetate or prepare this using acetyl acetone, etc., etc. Or they will simply tell you that I have this thing, you need to prepare this, and you can do that by using the Hantzsch method or the Paal-Knorr method or the Knorr method, etc., etc. So thank you for your patience, and I will be seeing you in the next one.